Henry Cialone. I'm the President and CEO of EWI. Really appreciate you inviting me here today to tell you a little bit about more efficient manufacturing. First, who are we? We're working on shaping the future of manufacturing through innovative technology solutions. So we're an inventor, we're a developer of technologies that we then deliver to industry. We develop manufacturing technologies that either improve product performance or reduce the cost of manufacturing the product. We work with clients to develop, optimize, qualify, test, and implement those technologies. We do a lot of collaboration with industry and universities to extend our capabilities so we can deliver complete solutions, and we commercialize technologies that deliver competitive advantage. So I was asked to talk a little bit about how do we think about energy efficiency in the space of manufacturing, and why manufacturing? Well, manufacturing tends to be pretty energy intensive, and so if you can be more efficient, then you can realize some significant savings. So we look at things that either increase the efficiency of the manufacturing process itself by reducing waste, increase the productivity of the manufacturing process. So in fact, I'll show you some examples where we increase the energy input, but we get more than an equivalent return on productivity of the process. So we do both by developing a completely new process. So let me give you some examples, if I can advance. Here we go. Okay. So in automobile manufacturing, I thought the Nissan automotive plant would be an interesting example to put forth. It's the first vehicle assembly plant to earn EPA's Energy Star rating. You can see that the electricity use in the vehicle assembly plants dropped over time, increased over time, but per vehicle dropped significantly. So what happened? Well, they made the building more efficient, which is an area that people often overlook. They changed behaviors. They did a lot of conservation efforts. Lean manufacturing principles were employed throughout the company, and then they introduced some technology. Painting process controls, motor efficiency and controls. They reduced or eliminated compressed air. They went to servo weld heads rather than pneumatic weld heads that were more efficient. And so they were able to realize through a lot of actions a lot of efficiency. Let's talk about another aspect of automotive efficiency, automotive manufacturing. As you know, cars are put together by putting a lot of spot welds. And historically, spot welds were tested by taking a hammer and chisel. Stick the chisel between the two sheets of steel, whack it with a hammer. If it's a good weld, it won't pop. And then you take a pair of pliers and squeeze the two sheets back together and move the car down the line. These days, there's a lot more very high-strength steel being put into the car so that they can achieve the CAFE standards that they need to achieve while also providing the crash protection. So if you try to hit one of those spot welds with a hammer and chisel, a good weld can pop. And if it doesn't pop, good luck squeezing those two pieces of steel back together. They're 5 times as strong as the last set. So what they do today, and you can see this is actually a photograph of a fireman with the jaws of life trying to rescue a person. We couldn't get a picture inside of a plant, but what they do is they periodically take a car off the line and tear it apart. And then they look at the welds and see if they're any good. Now the assumption is that every car after that's, if that has good spot welds, the next set of spot welds are good. But you really don't know that. It's a reasonable assumption, but it's still an assumption. And there's, more importantly, a lot of energy wasted, not only in tearing the car apart, but all the stamping energy, the welding, the steel itself, the delivery of the steel. So we came up with an approach to non-destructively evaluate these spot welds, taking the imaging technology that you use in the medical field, upping the energy involved in that, changing the materials models so we can interpret the signal that comes back, and we use a very, very small amount of energy, and we can test every spot weld in every vehicle. So that technology is currently being commercialized through a partner in Colorado, and you'll see that a lot of car manufacturers start to adopt it. I'll give you another example. There's something we call EWI Deep TIG. It's basically a mix of powders that are applied to the surface of a metal. And the idea is to change the profile of a weld when you're doing TIG welding. So this is where you're using a tungsten electrode, an inert gas, and you're adding metal basically by dabbing it. So it's kind of high temperature soldering. This stuff that we put together increases penetration of the weld by several fold. And what that does is rather than giving you a big wide weld with a lot of molten metal, you're getting a nice deep narrow weld with less molten metal. So melting less metal, there's less heat input, you're saving energy, you're also reducing distortion. So here's a couple of examples. The one on the left is a normal TIG weld with no deep TIG, a lot of, more than one pass, and a lot of energy being put into it, whereas when you've got this additive stuff, it's one pass and substantially reduced energy input. So let's talk about another kind of arc welding. This is using gas metal arc welding, where you're now feeding a wire through a gun and you're melting that wire through an arc. In this case, we've taken two wires coming in at the same time and changing the diameter of those wires so they melt with less energy input, and we can get very, very deep penetration, very, very good welds with, again, rather than a big puddle of molten metal, you've got a very narrow groove of molten metal. This is an example of that. You're taking the volume down of the metal you melt. Seems pretty simple, but to do that and also get good wetting of the molten metal on the base metal and get a good solid weld is a tricky thing to do. So this process reduces the energy per foot of fixed section weld by 77%. Another approach is to combine technologies. So we take lasers and we take arc welding and we put them together. And so you can see the apples to apples comparison. There's a lot of variables, so you have to try and hold as many still as you can. But basically what you're doing is you're taking a laser. A laser has very deep penetration, but it needs a perfectly fitted up joint. Arc welding doesn't need much perfection at all because it's dumping a pile of molten metal in there. But by putting them together, you can reduce the number of passes, reduce the amount of metal you're melting to get a good quality weld. Let's talk about something different. Let's talk about machining. This is one where we put more energy in, but we get more productivity out. So what we're talking about here is putting very intense ultrasonic energy into a conventional machining process. And when you do that, for reasons we have yet to figure out, you get much higher productivity. You can cut faster. You can cut harder metals than you could with the same tool. You get longer tool life, better surface finish, better accuracy. The tool doesn't walk. Why does all that good stuff happen? Well, basically, you're reducing the force required and the torque required. And by doing that, if you look at, I've done a stepwise comparison here, the monthly power usage for one machine with a conventional machining process versus with this Acoustech technology, you have significant reduction. Okay. Now, most people don't have one machine. They may have 20 on the shop floor. So if they do that, you can see significant difference still in the energy required. What's really cool is your productivity goes up. If you in this application, you could machine at 4 times the normal rate. So 4 times the productivity, you're now looking at much less power, much less energy per unit of output. But the reality is when you're in a manufacturing environment, there are upstream and downstream steps in the process, and so you have constraints. So in this case, the plant where we did this demonstration had a downstream constraint, so we couldn't go 4 times as fast, but we could go twice as fast. So net, we're using about 1/3 of the energy by applying this technology. Plus, that's another big plus, was there were reduced medical claims because the chip formation is different and people didn't get cut pulling these pieces out of the machine. Additive manufacturing, this is 3D printing. You've probably heard a lot about that in the news recently. This is one where you're, rather than taking a big piece of metal and machining 90% of it away so that you have a finished product, you're building it up one particle at a time. And so the energy consumption is substantially reduced. The big challenge here is you need to have a lot more work done to do the certification testing to be able to design with these kinds of materials. So the final piece I want to talk about is, there's always the question, do the cobbler's children go around barefoot? And do we believe in this energy efficiency? So I'll tell you a little bit about what we're doing at home. We've recently installed a solar roof, thanks to SB 221. Thank you very much. Made it easy to do, reduced some of the upfront cost by because we were able to sell our solar renewable energy credits to AEP. We financed it. We're a nonprofit, so we couldn't take advantage of the investment tax credit, but we could get someone else to take advantage of that and then share a little bit of it with us through the leasing package we got. We renegotiated our power pricing. We went into a demand response program. So we did an awful lot of stuff to change our energy profile. Lighting, we changed all the lighting in the parking lot, in the high bay, and throughout the building. A lot of reduced energy and savings that were significant. This is not an adjective, by the way, the second bullet. That's the name of a great company in Kentucky that makes a fabulous product, and you see a picture of it. What can I say? It's accurate. But we put these big-ass fans throughout the high bay. Well, what does that do? By recirculating the air, it makes you feel warmer or cooler, and it reduces the HVAC load, which is a big deal when you got high ceilings. And then this is really not about energy efficiency, but facility-wide surge protection just came along with the deal, which allowed us to protect our sensitive equipment. So in summary, that's the total annual savings are 2.5 gigawatts, gigawatt hours. So increasing the efficiency of manufacturing processes, I've shown you a few examples of how we do that. Increasing the productivity of the manufacturing process, showed you that with, for example, the acoustic machining, and some things that really provide completely new processes that achieve both. So, and they're powered efficiently. So thank you very much.